So, last time we met, we talked about iterative reconvolution and how to fit data. So, today we will try to learn two things. First is what do we fit the data to, and second, how do we know that the fitting is good or not. I mean, if we look at the data, looking at it, we might be able to say that this is a good fit or this is not a good fit. But the question is, computer does not have eyes. How does the computer know whether a fit is good or otherwise? But before we go there, let us discuss the data fitting models. Because after all, if you remember, we had said that in the simplest case scenario, we have a single exponential decay, and we said that in more complicated scenario, the most popular way of fitting data, not necessarily always the correct way of fitting data, is by a multi-exponential function. And I think we are more or less familiar with this kind of functions. The first one here, I of t is equal to I at 0 multiplied by e to the power minus t by tau. This is the simplest way you can fit the data. I out at t is the fluorescence intensity at time t, I at 0 is the fluorescence intensity at time of excitation or 0 time, and tau is a lifetime. So, this is essentially the integrated rate law for a first order process. It cannot get any simpler than this. But then we said that it is not necessary that life will be so simple and we can have more complicated data. So, as the first kind of complication we can think of is in the form of a multi-exponential data. Let us say you have several independent decay pathways. Then what do you get? I at time t after excitation is the same I at time 0, but now this is multiplied by not one exponential term, but rather a linear combination or weighted average or weighted sum of several exponential terms. I can have several values 2, 3, 4, 5, 6, 10, 100, 200. In principle, it can have any number, and then you will have as many exponential terms and as many amplitudes. Square of amplitudes, as we know, gives the contribution. Now, the thing is, if you increase the number of exponential terms, generally you would get a better decay, a better fit, because there is something called over parameterization. So, first question to ask is my decay single exponential or is it not? How do we know whether it is single exponential or not? The best way to do that is to make a semi-log plot where y axis counts is in logarithmic scale, x axis time is in linear scale, and have a look at it. What will the shape of this curve be if it is a single exponential decay? It is going to be a straight line, and if it is not a single exponential decay, then it will not be a straight line. So, that is the first question to ask. So, if it is a straight line, then actually if you fit it to 2 or 3 exponential terms, then it will still fit very well, but it will not make any sense. So, first thing that one needs to do is a visual inspection, and by visual inspection the first thing to ask is whether it is at all exponential, single exponential, or whether it is more complicated. Of course, looking at the decay, you will never be able to tell whether it is bi-exponential or tri-exponential or what. You can only tell whether it is single exponential or not, right. Now, what are the implications of these terms? Let us start with the discussion of the single exponential decay, tau. We have discussed tau already. So, what is the meaning of tau? Can you tell me? Tau is called the lifetime, that is right. Why is it called the lifetime? Because it is average time spent by the molecule in its excited state, and that is something that was given to you as a homework. You are supposed to work it out. It is worked out in standard textbooks like that of Lakovich, Principles of Fluorescence Spectroscopy by Lakovich. And then this lifetime tau is also related to some other quantity that we have discussed very early on in this course. And what is that quantity? So, let us put it this way, if lifetime is longer, do you expect the fluorescence to be more intense or less intense? Then you expect it to be more intense. Why? Because of this simple relationship that phi f, the fluorescence quantum yield, is equal to Kr multiplied by tau. What is Kr here? It is a radiative rate constant. A word of caution here, very often in literature you will see people say it is radiative rate. but let us not forget that it is a radiative rate constant. So, please be careful and remember it is a rate constant and not rate, alright. Now, this radiative rate constant is related to some fundamental quantities that we might have studied in spectroscopy courses during our MSc or something. Can you tell me what the radiative rate constant is related with? Einstein's coefficient, which one? Actually, if it is related to A, it will be related to B also. Einstein's A coefficient is the coefficient for spontaneous emission, but then that is also linearly related to B. And what is B related to? B, when you say B, Einstein's B coefficient, it is for stimulated transition between two states, right? Upward transition or downward transition. So, what about upward transition? Is there a B associated with it? They are actually equal, right? B12 equal to B21. In terms of experiment, what is the experimental quantity that is associated with B12, where 1 is the lower level, 2 is the higher level for absorption? The Einstein's B coefficient for absorption, which experimental quantity should it be related to? Yes, little louder please. So, what is it called? Okay, of course, it is related to transition moment integral, but that is something that you get from quantum mechanics. What is it that I can get using some instrument experimentally without knowing any quantum mechanics perhaps, that will be related to the radiative rate constant? Molar extinction coefficient or molar absorption coefficient, that would be related to the radiative rate constant, okay. And there is a relationship between the two, which once again you can study. We are not going to go into the detail right now. Now, so the good thing about knowing fluorescence quantum yield from steady state measurement and lifetime from a time resolved measurement is that you can work out the radiative rate constant. More importantly, 1 minus phi f is equal to k nr multiplied by tau. So, you can work out the non-radiative rate constant. So, as we go further in our discussions, we will see that we will more and more want to know what is the rate constant associated with some non-radiative process that takes place in the excited state of a molecule, and this is how we will get the answer. Now, the problem is we get the answer very nicely if it is a single exponential decay. The moment it is multi-exponential, situation becomes complicated. So, when it is multi-exponential, what is the implication of AI? What is the implication of tau I? Let us ask that question now. And the answer is AI multiplied by tau I gives you the contribution of the ith component to fluorescence intensity. Now, this point needs to be understood very clearly in order to go further ahead in the discussion of time resolved fluorescence spectroscopy. See, AI into tau I, say I is some component, right. So, let us think like this, that we will use this example once again a little later. Let us think that there are two components, tau 1 and tau 2. Tau 1 is because of a fluorophore that is free, and tau 2 is due to the same fluorophore that is bound to say cyclodextrin or protein or something like that, and tau 2 is longer than tau 1. Okay. What will be the intensity? Will the intensity be more? Will the intensity be less? That depends not only on tau 1 and tau 2, but also on how much of it is bound, how much of it is free. Let us say only 20% of the fluorophore is bound to cyclodextrin, and let us say for the free form of the fluorophore lifetime is 1 nanosecond, for the bound form lifetime is 10 nanosecond. What will be the intensity if 20% is bound, and what will be the intensity if 80% is bound? Naturally, intensity will be much more when 80% is bound. Where does that come from? That comes from here, that contribution of the ith component to fluorescence intensity is actually AI multiplied by tau I. Tau I, remember, is an intrinsic quantity, lifetime characteristic quantity, but AI is the contribution, and this can have actually severe implication. Suppose think of a nanoparticle that we have made, which is almost completely non-fluorescent. The only fluorescence that it is, well, only photoluminescence it has is due to some trap states, right. So, let us say that the time for recombination of electron and hole in that nanoparticle is something like 1 picosecond. 1 picosecond is a small time, so fluorescence intensity should be low. But let us say there is some trap state and concentration of trap states is really very low, but lifetime of the trap state is 100 nanosecond. What will the photoluminescence of this nanoparticle be due to? Mainly the trap state, which is very few in number, or the intrinsic bandage recombination of electron and hole, which is taking place all the time. In photoluminescence, you will actually see a much greater contribution of the trap state because its lifetime is 100 nanosecond. But this is only an example. There are cases in which a small ai can be overcome by a large tau I, like what we just discussed. There are cases in which a small tau I can be overcome by a large ai. Think of an extreme case. Think of, say, warfarin is a very common fluorophore that is used in fluorescence study of protein. Lifetime of free warfarin is something like 100 picosecond. Lifetime of bound warfarin is about 2 nanosecond. Now let us say I have very little protein, almost all the warfarin is free. Will intensity be high or low? It will be low because then this tau I, tau 1, 100 picosecond, that component will have almost 100% contribution, ai will be large for it. But when it is bound to protein, even if say 10% of it is bound to protein, then what will happen? The contribution, the fluorescence intensity will be much more because lifetime has now increased from 100 picosecond to 2000 picosecond, 2 nanosecond, 20-fold increase. So, what the composite intensity will be is governed by the relative values of amplitude as well as lifetime. So, ai tau I, remember, is the contribution of the ith component to fluorescence intensity. So, what is steady state then? What is the steady state intensity? See, when we talked about a single exponential decay, we could easily correlate the quantum yield, which is a measure of steady state intensity, with lifetime. Can we do some such correlation in case of multi-exponential decay? Let us see. In case of multi-exponential decay, will you agree with me, or for any decay actually, I hope you agree with me when I say that the steady state intensity is integral of intensity at some time t from time 0 to infinity after excitation. Of course, when I say 0 to infinity, I write infinity only to make it a general statement. It is not really infinity. For all practical purposes, what is infinity? Infinity is the point where the decay has become almost 0. See, if it is an exponential or multi-exponential decay, it becomes 0 asymptotically. But for all practical purposes, suppose I at time 0 is 5000 counts, and then you go to 10 nanosecond, and there you see that the intensity has become like 5 counts. So, 5 is much lesser than 5000. So, you set it to almost 0. So, what we are saying is intensity of steady state is really integral of I of t dt for limits 0 to infinity of time, or rather we can say that it is the area under the decay. Of course, we are talking about a particular wavelength. Is this understood? That steady state intensity at any particular emission wavelength is the area under the decay, or it is the integral from 0 to infinity of I of t. Then let us substitute the expression. Since I at 0 is a constant, it comes out, and I can take this summation outside the integral. So, I get I at time 0 sum over I ai integral e to the power minus 1 by tau I dt. Okay. And an advantage of setting the limits from 0 to infinity is that this becomes a standard integral, solution of which is known. And when we put the solution, we get something like this. I steady state is I at time 0, I missed that 0 in brackets here, sorry about that, this 0 has become small, I at time 0 sum over I ai tau I. Or we can write I at time 0 is equal to I steady state divided by sum over I ai tau I. So, here is a correlation between steady state intensity and the lifetimes. The take home message is that it is not enough to look at only lifetimes, you have to look at their amplitudes as well, contributions as well. But actually it is better to stop here and not get over enthusiastic and take it a little further, like say 80% of people do in fluorescence spectroscopy. So, what you see is that almost all the decays are fitted to multi-exponential function, and everywhere people happily work with what they call average lifetime. This thing that you see, average lifetime, is sum over I ai tau I divided by sum over I ai. Dimensionally this is fine, right, because this will have the magnitude of time. But this amplitude weighted average lifetime, to be honest, has no meaning other than steady state intensity. So, it basically gives you a measure of steady state intensity, and if you are going to talk about steady state intensity only, then what is the point of doing a time resolved measurement in the first place? So, as far as possible, it is better to avoid using average lifetimes, and also this is not really average lifetime. What is really average lifetime is this: intensity weighted average lifetime, sum over I ai square tau I square divided by sum over I ai tau I. So, you see here the denominator is actually the total intensity. So, this average lifetime may have some meaning. So, it is related to the area under the curve, but then from here trying to work out radiative rate constant, non-radiative rate constant is not a very sensible thing to do, because after all you are saying that different lifetimes are associated with different processes which would have different non-radiative constants or radiative constants or whatever. So, if you take an average lifetime, all that individual information and implication, everything is lost. So, if we have to work with multi exponential decay, if we have to use average lifetime for some reason, then let us not try to take it too far and work out the rate constants in the first place. Now, they are not completely useless. This amplitude weighted lifetimes actually are used when you talk about, say, Foster resonance energy transfer. That is where this amplitude weighted lifetime have some application, but generally it is not really correct to call this the average lifetime. This is average lifetime if at all, and it is not very useful. That being said, let us move over to something that is more complicated and therefore closer to reality many times. So, next model we want to discuss is distribution of lifetimes, and this distribution of lifetimes is a much better model than sum of exponential. But the problem is this: when you do sum of exponential, then what you imply is that you have that many lifetimes discretely, but sometimes that may not be the case. Suppose you have a range of microenvironments, you do not have a 0-1 situation, you have some kind of a microheterogeneous medium where you have graded polarity or graded viscosity. Say there is a polymer, right, and maybe at the core the polymer is very dense, and on the outside it is not dense at all, and let us say your fluorophore is distributed from core to the end, many places. Now, a multi exponential model is not valid. If it is simply bound versus free, then it is valid. But even when we go back to this bound versus free model that we used, think of some fluorophore that is bound to a protein. It is not always the case that it is bound specifically to one site and experiences one kind of environment. More often than not, you can have non-specific binding, and if it is non-specific binding, then even bound fluorophores actually experience different kinds of environments, or in other words, they experience a distribution of environment. When we say environment, it might be convenient if we talk in terms of, say, polarity. We are all familiar with, say, dielectric constant, even though dielectric constant is not a good parameter of polarity in micro heterogeneous media, but still for the sake of simplicity let us say dielectric constant. Let us say our fluorophore is bound to a protein non-specifically and it experiences a range of dielectric constants. The modal dielectric constant let us say is 20 and there is a distribution say 20 plus minus 5, that is a distribution, and a distribution is going to have some kind of a shape. It can be a Gaussian distribution, it can be a Lorentzian distribution, it can be two-sided exponential, it can be whatever, but some distribution function may be there. For such a case, a better fitting function than the mundane multi-exponential model is distribution of lifetimes. And here you need to look at the function a little carefully, because it might actually look like a multi-exponential function to the untrained eye. I at time t is equal to 0 to infinity alpha tau e to the power minus 1 by tau t by tau d tau. Please note it is not dt. Of course, an integration is a summation, but here alpha tau means distribution function of lifetime and we are integrating over lifetime. Okay. I have not written the distribution function explicitly because you might have to use different distribution function depending on what kind of system it is, but this is more often than not a much better fitting model than a multi-exponential one. See, a multi-exponential function might fit your decay. I am not saying it will not fit, because as I might have said in this course, I have actually seen an elephant, shape of an elephant drawn by a clever combination of 30 exponential functions. Using a sufficient number of exponential functions, perhaps you can draw a self portrait also, if you play with the amplitudes correctly and if you play with the shifts correctly. But that would not mean anything. Is an elephant made up of 30 exponential functions? I mean, does it even make sense? It is funny, right? It is laughable. Similarly, just because your decay might fit to a multi-exponential function does not mean that it is the correct model to use. And if you are going to do a quantitative study, if you are going to extract as much juice as you can from your lifetime data, then it is important to go beyond the convenient multi-exponential model and think what your system is like and think what kind of fitting model would be appropriate for your system. And fortunately, this distribution of lifetime and all, they actually come with commercial data fitting packages now. In our lab, we have two programs, one is from PicoQuant, the other is from IBH, which is now Horiba Jovenivan. Both the programs, I believe, have this option of fitting to a distribution of lifetimes. It is more difficult, it takes more time, it requires more playing around, but it is doable. Of course, if you use a better algorithm, then it is easier to do it, but maybe we will postpone that discussion until we talk about actual data fitting and goodness of fit. Let us move on. This distribution of lifetime is often a better model to use depending on what kind of system you are looking at. But as we discussed, it is also a more complicated model. Multiple exponential is easier, in fact even fitting is easier. So often what we do is, and these programs usually have a provision of letting you do it, often what you do is you try to get away with the trouble of using explicitly a distribution function like Gaussian, Lorentzian, etc., by instead using a large number of exponential function. Of course, at this point it might be a little confusing, because 10 minutes ago I was saying not very kind things about multiple exponential functions, and here I am saying that you can fit the data to a large number of exponential functions, but bear with me for a while, it will start making sense. So what you do is you fit to a large number of exponential functions, but what you do is that you tell the system what the lifetimes are. So, you fit to not 2 exponential or 3 exponential function, fit to 100 exponentials. If your computer and if your program are good enough, fit to 1000 exponentials and use a wide range, something like this. Use fixed lifetimes. So, the way you fit now is that you say that the lifetimes I have are 0.1 nanosecond, 1 nanosecond, 10 nanosecond, 100 nanoseconds, so on and so forth. Usually they are arranged logarithmically, not 10 after 1, but logarithmically, so that you can look at small lifetimes as well as large lifetimes. Okay? And you fit your data to this function, where all these tau I values are forcibly preset. So, what is the only play you have? What is the only parameter that is going to change? The amplitudes, right, AI. So, what you will get is, you will get, if you are using 100 lifetimes, you will get 100 amplitudes. Now, what you do is, you plot the amplitude against lifetime, right, and then you get plots like this. This is actual data taken from this 2000 Cell Molecular Biology paper. So, here you see they have looked at different emission wavelengths, 300 nanometer, 320 nanometer, 380 nanometer. Note the y axis amplitude, note the x axis lifetime, and here of course they have not gone out to 100 nanosecond, rather they have gone from less than 0.1 nanosecond. Now, do not ask me how they did it using time correlated single photon counting, up to say 10 nanosecond. And if you look carefully at the x axis, can you see that it is logarithmic? It is logarithmic because you want to look at 0.1 nanosecond kind of lifetime, as well as 5-6 nanosecond kind of lifetime. If it is not logarithmic, you are going to miss this. So, you see, let us not worry about what FKBP59 is, it is some kind of a protein, but what you see is at 380 nanometer, you have two kinds of lifetimes, something that is very small, 0.1 nanosecond or so, something that is quite large, say what is this, 2, 3, 4, 5, 6 nanosecond, and there is a distribution about 6 nanosecond, there is a distribution about 0.1 nanosecond as well. That means there are, first of all, there are two broad kinds of environments. Moreover, within each of the kind of environment, there are subdomains. That is why you get this distribution. And one reason why, if you have the capability of fitting your data to 100 exponentials, one way this approach is better than using an explicit distribution is that, how do you know what the distribution is? How do you know that it is Gaussian? Look at what we see here. Is this Gaussian? It is actually log normal kind of distribution. But there is no way in which I can know beforehand whether it is going to be Gaussian, Lorentzian, log normal, what, right. So, good thing about fitting your data to many exponential model where lifetime is fixed, amplitude is varied, and you make a plot of amplitude versus lifetime, is that you do not care about what the kind of distribution is, but it comes out automatically in your result, right. Here you see that the short lifetime, but of course, this may not be log normal also, because do not forget the x axis is not linear, it is actually logarithmic. So, I do not know what it is, but the point is I am not working with any particular kind of distribution. Whatever is the distribution is expected to show up in the process. Now, when you go from 380 nanometer to 320 nanometer, now what do you see? Now, this 0.1 nanosecond kind of component is completely gone, rather you have a broad, in fact, if you work out the area under this one and this one, I do not know which one will be more, and I do not know even more because the scale is logarithmic. But here you have quite a good distribution around say 0.3 nanosecond. So, the 0.1 nanosecond component is gone, you get a 0.3 nanosecond component and you have this distribution there. We have something new between 1 and 2 nanosecond, and that also has a broad distribution, and whatever you had earlier is there. But now what it appears is that this thick edge that you had has given way to a completely new distribution that is there. Okay. I do not know what the system is, and at the moment I do not care. I am just trying to show you some data, and trying to discuss what this data would mean. Now, when you go to 300 nanometer, what do you see? You see that this 0.3 nanosecond component that had come, that is now the major component. It has some distribution, but it is not so much. Of course, you can see that here full width half maximum is several nanosecond. Here full width half maximum is hundreds of picosecond. Of course, you have to work out percentage. So, now this 200, 300 picosecond component is the major one. This long component has become very small, and this one has also gone down compared to what it is. Okay. So, here I hope we have been able to convey that by doing this kind of data fitting, we actually get a wealth of information that we do not get if we mindlessly fit our data to double exponential or triple exponential model and resort to your average lifetime. That means nothing. This actually tells you what your system is like. Okay. So, what we have learned so far is that more often than not, you might have to work with a system where you have a distribution of lifetimes. The one way of handling distribution of lifetimes is to use a specific distribution. Danger of that is that may not be the case. Other way of doing it is go back to good old multi exponential function, but this time plot amplitude versus lifetime, and do not stop at 2 and 3. Since you are doing multi exponential, go all the way and fit to 100 exponential, but for that you have to have a good computer, you have to have stout algorithm. We will talk a little bit about algorithm towards the end. Okay. But here we take a break and we come back in the next module and continue with more data fitting models, and there we also learn about goodness of fit.